In this video, we're going to talk about the magnetic force on a current carrying wire, also known as the Lorentz force, sometimes written as F subscript B, B for magnetic force, sometimes F subscript M. You'll see all of those. So that's the big thing we want to figure out, is what is our method of determining how much force will a current carrying wire feel in a magnetic field. And this all comes from the fact that we know a current carrying wire generates a magnetic field and can cause, like a compass needle, to deflect, right? That was the first thing. That was the Oersted example, talking about currents generating magnetic fields. But if a current can generate a magnetic field that can push a magnet around, it stands to reason from Newton's third law that if there's something that you can apply a force to that magnet, then that magnet must also be able to apply a force to the source of that push, and that would be the current carrying wire. Now, in this case, in this picture, the wire isn't going to move because it's all tightly wrapped, because it's got other forces. But you can see this effect if you use an old style Edison bulb with a big carbon filament that's kind of loose and isn't, like the more modern incandescents have a tightly wound tungsten. You can't really see this, but if you take a strong magnet, you can actually get it to deflect and vibrate because vibrate because it's an alternating current, but if it were direct current, you would get it to deflect. You can also do a thing where you take a big strong magnet, you put a wire in the middle of it, like this second picture, and then you you turn on the current, and the wire will feel a force in a direction. I can actually show you an example of that, which I will do now. So here we've got our demo from an MIT lab. So there's a big strong magnet. We've got a 12-volt battery, so it's going to be a big current through this wire. Big old switch. Notice it's protected because it's a lot of current. We got a long wire in there. As shown, that's our big strong magnet. Very exciting. So they're attaching the battery. Just make sure it's ready, and then the knife switch. Right. Pretty exciting. Notice when the current went in the opposite direction, it was pulled down instead of up. So the fundamental idea here is that when there is current flowing through a wire, it experiences a force. And so we want to talk about this force. The force has a couple of characteristics. One, it's perpendicular to the current, and it's perpendicular to the external magnetic field that was applied to it. So if you see in this diagram, you've got the current direction kind of coming down and out of the page a little bit. We've got the magnetic field going north to south across that, and the force is up. And this is because this force comes out as a cross product. And that means that if you were to apply a magnetic field along the direction of current, you would get no force. So here's the actual formula. We say that the magnetic force, of the Lorentz force, is I/L cross B, where I/L, like the current times the length of the wire that's in the magnetic field, is that direction vector is the direction of the current, and the B is the magnetic field direction. ILB sine theta is how you get the magnitude. You also see on your AP equation sheet an integral because this could be any length of wire. And then there's this angle, of course, in there. The units of this force, as I mentioned in a previous video, are Tesla. Newtons per amp meter is the force is, of course, in newtons, but the force is in, the magnetic field is in Tesla, which is a Newton per amp meter. And if you multiply that by an amp and a meter, which is what IL gives you, you get newtons. So here's an example of how this behaves. A wire carries 24 amps of current. This is direct current, like from a battery. Between two poles is kind of like a trolley wire that you might see, the green line going under in Boston. And there's a magnetic field from the Earth, which is given a direction, 10 to the negative fifth Tesla, pretty small. What is the magnetic force direction and magnitude on the wire? Well, for the direction, we'll have to use the right-hand rule. And so the way that works is this is a new right-hand rule. The basic premise is that your thumb is still the current, just like it was before. Your fingers are the B field, and your palm pushes in the direction of the force. So if the B field is into the page and the current is across to the right, then the force would be up. Just like that. We can calculate the magnitude. The sine is 0. Theta is 90 degrees, and the sine of theta is 1. Then we can plug in all of our values there, and you get about 0.021 newtons. Not a big force, right? Remember, a Tesla is a pretty big unit, and so in order to get a full newton of force, you might need something like a full, Tesla of magnetic field. So the other thing that we can think about is current carrying wires. They can either, if they're next to each other, they can either attract or repel each other. And so we want to think about how that works. So the basic premise is if you put a single wire in a page, we use the first right-hand rule, or the little right-hand rule, that says on the right-hand side of that wire, kind of where the current's going up, the magnetic field is in. And then as you curl your fingers around on the left-hand side, the magnetic field is coming out. And so if you were to place a second wire also going upward here, I'm not going to draw the magnetic field that this wire generates. I'm going to say, well, the first wire, current 1, generated this magnetic field. And then this second wire is going to experience with our new right-hand rule where the magnetic field is in and my thumb points up, and it's going to be pushed to the left. Pushed to the left, right? And that's what happens. And that would be an attractive force. Now, if that's true, then according to Newton's third law, I1 must also be attracted. Now, we could redo the problem. Instead of drawing the magnetic field for current 1, we could draw it for current 2 and then figure out the force on current 1, and it would be the same exact thing. The wires attract. So parallel currents attract, anti-parallel currents repel is the big idea here. It's good to know, good to remember, but it's not vital. You can always figure it out by drawing the magnetic field from 1 and then talking about which way that wire would feel a force. So I have another quick video demo for you here that I don't think, it's not going to play. All right, so this is another one of these demos. Again, thank you, MIT Lecture Demonstration Group, Physics Lecture Demonstration Group. We got 2 wires, right? And they have current going kind of up and down. The circuit in series pulls switch forward, circuit in parallel pulls switch backwards. So it's wired up so that you can get this thing where they're parallel or anti-parallel. So starting with the parallel or the anti-parallel, they repel. Parallel, they pull together, right? Repel, pull together, right? So we get those nice examples. You see a close-up, currents going in the same direction, or versus currents going in opposite directions. All right, kind of wrapping things up here. We want to calculate the magnetic field due to one wire at the location of wire 2 is always our first step. So in this case, right, wire 1 generates a magnetic field. We're going to draw an Amperian loop around it. Think about what the magnetic field should be at the position of wire 2. That's B times 2 pi r for the magnetic field times the integral around the loop equals mu naught I1. Right, so magnetic field is mu naught I1 over 2 pi r. Sorry about the bell. And we can calculate that value. Once we've done that, we say, well, there's a magnetic field into the page, according to the right-hand rule, from 1 on 2. And now we can use our new formula that says FB equals ILB sine theta. Is this current 1 or current 2 in this case? In this case, it's current 2, because that's the wire experiencing the magnetic field. The L's cancel out, and you end up with a repulsive force of about 8 times 10 to the negative 5th newtons per meter. Notice I put L over on this side. We could, if we knew how long the wires are, we could actually talk about how much force in total there is, but this is a more generalized solution. Another cool thing that the magnetic force can do is it can put a torque on a current carrying loop. Because if you have a loop going around, right, on one side it would be up, one side it would be down, it would cause it to go. And you could use multiple loops of wire here. And this is the essence of creating a motor. This is basically how it works. Current flows through, we get a motor to spin. And then we use this thing called a commutator so that the current doesn't flow the wrong way, so it always spins in the same direction. We also use this for what we call a galvanometer, which is basically a meter. We can have magnets, and the more current we run through it, this is basically how you get like an ammeter, a current meter. So that's it. We can cause a force on a current carrying wire by putting it in a magnetic field.